minus 1 plus an y raised to n. So here we see that in each of the terms, the degree of this term is n. Similarly, the degree of this term is also n, because you have x raised to power n minus 1 and y raised to power 1. So when you add them together, you get n. Similarly, the degree of this term, the power of x is 1, power of y is n minus 1. So total is n. And this is a degree, this is also degree of n. So in this above expression, we see that all the terms, each of the term on the right hand side of this equation has the same degree. Every term has the same degree n. Such type of equation is known as homogeneous equation of degree n. Okay. Now from this, what we can do is we can from this expression on the right hand side, you can take y, or let us say x raised to n, common. So when you take x raised to n, the first term will be a naught, second term will be a1 into y by x, third term will be an minus 1 into y by x raised to power n minus 1, and the last term is an into y by x raised to n. Okay, so when you take x common, you get this equation. Now in this expression, we can say that this is a function of y by x, and let us denote this function by g. So you can write this as g1. So let us denote this function by g1. So you can write this as a function g1 of y by x. Okay, so this you can write this in this way. X raised to n will come from here, and this expression is g1, the function g1 of y by x. Okay. Now instead of taking x raised to n outside, if I take y raised to n outside, so from here, if I take y raised to n outside, then I will have an. Let us start with this last term, an plus the second last term. This is an minus 1, and this will be x by y. And then dot dot dot. This term can be written as a dot 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 a1 x by y raised to n minus 1, and this term, this first term, is a naught x by y raised to n. Okay, so that means we can say that this expression, this is a function of x by y, and let us denote this function by g2. So we can say that this expression is a function of, x by y. This is a function of x by y, function g2 of x by y. So that means this whole thing can be written as y raised to n g2 x by y. Okay, so this is what is written here, this g2, what is written here. Okay, so when you take x raised to n outside, you get x raised to n g1, a function of y by x, and if you take y raised to n outside, then you get y raised to n into g2, which is a function of x by y. Okay, so from there we can say that a homogeneous function for f is a function of homogeneous function of degree n if f can be written as x raised to n into a function g1 of y by x, or you can say that f is a function, homogeneous function of degree n, if f can be written as y raised to n into g2, a function of x by y. Okay, so this is also these are, this is also another way to define the homogeneous function. Now we have another way to say the same thing. A function is called homogeneous function of degree n in x and y if it can be written, if this equality holds. F evaluated at lambda into x, lambda into y is same as lambda raised to n and f value times f evaluated at xy, where lambda is not 0. And this should hold for all real value, all real number lambda, and for all x and y coming from R2. Then also you can say that the function is homogeneous. Okay, so using this definition, we can visit some examples. So before that, we have one remark. If lambda is equal to 1 by x, that means in this definition, if I take lambda is equal to 1 by x, then on the left hand side you have f1 and y by x, and on the right hand side you have 1 by x raised to n fxy, and this implies fxy is equal to x raised to n f1 y by x. Now we can call this, we can rewrite this as a function. We can rewrite this in this way. Okay, you can say that this f is a function g1 of y by x, and therefore you get the relationship fxy is equal to x raised to n g1 y by x. Okay, so whether you say that whether you take this as the definition or this as the definition, they are equivalent. Okay, then similarly, if I take lambda is equal to 1 by y, similarly if you take lambda is equal to 1 by y, then this will reduce to this form. Okay, so you can take this also as the definition, right? So whatever is convenient for you, for your calculation, you can use that. So if I ask you to check whether the function is homogeneous function or not, you can use either this one or this one or this one. All three all three will lead to a homogeneous function of degree n. Okay, so let us consider an example. So let us consider 4 functions. One, this is second one, third one, and fourth one. Now clearly the first function is in this form, in this equation form. Okay, so this is a homogeneous function, and the degree of this function is 2. This is a homogeneous function of degree 2. Both the terms have degree 2, x raised to 2. The degree of x raised to 2 is 2. Degree of 2 into xy is also 2. You add the powers of x and y. Okay, so this is the first function is a homogeneous function of degree 2. Now the second function Second function you can check.
Is also but with 0
Yeah,
degree.
it is also a homogeneous function of degree 0. You can use this form here. So for the second function, basically this is x raised to 0, and what is g1? G1 y by x is tan inverse y by x. Okay, so x naught, x raised to 0 into tan inverse y by x. Okay, so this is also a homogeneous function of degree 0. Okay, the third one is a homogeneous function of degree -2. So how you do this? What you can do is you can from the third one you can say that this can be written as you take y squared or maybe x squared outside from the denominator. So you have x squared 1 plus y by x whole square. Okay, so this means you have you have 1 over x raised to 2 and 1 over 1 plus y by x raised to 2. This I can treat this as a function g1 of y by x. Okay, and this x raised to 2 can be written as x raised to -2. Okay, so if I compare this with this form, then the value of n is -2. From here I get n is equal to -2. So we can say that this function is a homogeneous function of degree -2. Okay, now the last one also you can check easily. Now consider this last one. So here also you can write this as this is equal to root under xy divided by, you can take let's say x squared outside, so 1 plus y by x whole square under root. Okay, and from here we can write this as y by x under root into 1 by 1 root under 1 plus y by x whole square. Okay, so this means I can take this as a function of y by x. I can write this as g1 y by x, and you can say that this is the power of x is 0. Okay, so this can be written in this form. So from here we get n is equal to 0. So this means this is a homogeneous function of degree 0. Okay, so this is how you can check whether the function is homogeneous or not, and you can easily, if the function is homogeneous, then you can easily identify the degree of the function. The function here, this function is not a homogeneous function, right? So because you cannot write this function in the given form. Okay, so this is not a homogeneous function. Okay, now we have this class work, so you can try at home to check whether this is a homogeneous function or not. The definition of the homogeneous function can be extended to a function of more than uh, two variables as well. Okay, so for
Yes.
in the case of three variables, for example, f(x, y, z) is a homogeneous function if fxyz is equal to x raised to n, you take x common, so you get x raised to n, and some function of when you take x common, you divide y by x and z by x. So that means you get some function of y by x and z by x, which we denote by the function phi. Okay, this is one way. Similarly, you can write y raised to n, some phi tilde, and when you take y raised to n outside, you write this as x by y and z by y. Or you can also say that this is z raised to n, some other function phi double tilde, where you have x by z and y by z. All right. So this is for the case when the function is of three variables. Otherwise, you can also say this last form, that f evaluated at lambda x, lambda y, lambda z is same as lambda raised to n times f evaluated at x, y, z. And n gives you the degree of the homogeneous function. And then you can generalize this for a function of n variables. Okay. So this is all about homogeneous function. Now we go to a very important result on homogeneous function, which is known as Euler's theorem. This theorem says the following. Let f be a homogeneous function of degree n in variables x and y, such that its first derivative and the second partial order derivatives. So that means for what is first partial order derivative? df del f del y, and second order partial derivatives are, these are second order partial derivatives. And I am putting this equality here because if the partial order derivatives, first and second order partial derivatives are equal, then the mixed order partial derivatives are equal. Sorry, the first and second order partial derivatives are continuous, then the mixed order partial derivatives are equal. Okay, that we have seen in our last lecture. Okay, so here we are given these assumptions. What are the assumptions? First assumption is f is homogeneous function of degree n. This is first thing. And the second assumption is all these partial derivatives, first order partial derivatives. There are two first order partial derivatives, derivative with respect to the variable x and the derivative with respect to the variable y. And we have four second order partial derivatives, differentiating twice with respect to variable x, differentiating twice with respect to variable x and y both. You can interchange the order of derivative, but due to continuity they will be same. So you have four. Okay, so all these first order partial derivatives and the second order partial derivatives are continuous. Okay, so if these two conditions are satisfied, what are the conditions? F is a homogeneous function of degree n, and first order partial derivatives and second order partial derivatives are continuous. If these two assumptions are satisfied, then we have these two equalities given in equation 6 and 7. Then we get this one as well as this one. Okay, the proof is very elementary, although the proof is not needed, but we can go through the proof quickly. So what is given to us? F is a homogeneous function of degree n. So use this fact. F is homogeneous, that means fxy can be written as x raised to n times some function, let's say g of y by x. Okay. Now differentiate this. Differentiate this with respect to x first, both the sides. Okay, so we are at this place. So we differentiate this with respect to the variable x. So obviously by keeping this is partial derivative, so you keep y as a constant and differentiate this with respect to variable x. So you can apply the chain rule. So derivative of x raised to n will be n into x raised to n minus 1 times the function g of y by x, and then plus x raised to n, and then apply the chain rule here for function of one variable. So this will be derivative of g, which we denote by g dash, and then derivative of y by x with respect to x. So this will be minus y by x squared. Okay, so after rearranging the terms, you get this. And similarly, differentiate this with respect to y. Differentiate with respect to y, you will get this equation. Okay. Now simply get these two equations. Now you simply multiply this first equation by x and the second equation by y. So on the left hand side, where you multiply this by both the sides, you multiply by x. So left hand side is x uh, partial derivative with respect to x, and in the second equation, this is y partial derivative with respect to y, and then you add them together. So when you add them together, you get on the left hand side, you get this quantity. Okay. On the right hand side, you have this. When you multiply this by x, this will become n x raised to n. This will become x raised to n minus 1. Okay, and when you multiply this equation by y, you get x raised to n minus 1 into y. Okay, and you add them together. Okay, so what we observe? We observe that uh, this term and this term will cancel out. Okay, so you are left with only this term, which is this. Okay, and we have already said that f is equal to x raised to n g y by x. So this quantity is equal to this quantity is f using this relationship. So we can say that this is equal to n into f. Okay, this proves equation 6. Okay, so simple derivative. You simply find the derivatives and you get some multiplication and addition, and you get equation 6. And now once you have equation 6, you can differentiate this equation, both the sides, first with respect to x and then with respect to y. So you get, when you differentiate this equation with respect to x, both the sides, you get this one. And when you differentiate the equation 6 with respect to the variable y, then you get this second equation. Okay. And now what you do is you multiply equation 8 by x and equation 9 by y, and then add. Okay. So let us see what we get. This term will become x square, second order partial derivative with respect to x. So we write it here. This term will be x times first order partial derivatives. You write it here. This term will be x into y, second order mixed order partial derivatives. You write it here. And the right hand side will be n into x. So, and first order partial derivatives. You write it here. Okay. Similarly, from the second equation, the equation 9, you have x into y, second order partial derivative. So write it here. Then you have y into first order partial derivative with respect to y. Then you have y square, second order partial derivative with respect to y. And the right hand side is n into y and first order partial derivatives. Okay, so write it. All right. And then you can gather the sum of the terms. So what you do is you can see that you can take n outside. Let's look at this term. Look at this term on the right hand side. You can take n outside, so you get this. This becomes your right hand side. And from the term on the left hand side, you combine these two together. This term and this term. You combine them together. And then use equation 6. So what is equation 6? This is equation 6. So x partial derivative with respect to x plus y partial derivative with respect to y is equal to n into f. Okay, so just use this one. So when you combine these together, this will be equal to n into f. And on the right hand side, you get one n is already there. The term in the curly brace will give you n into f. So you get n square f. So this term will become n square f, the term on the right hand side. Rest of the term, we do not do anything with the rest of the term. And the second thing that we observe is that since the second order partial derivatives are continuous, so mixed order partial derivatives will be equal. Okay, so this one can be combined. These two terms can be combined, so which can be written as this one. Okay, so what we have now. So let us see what we have now. This term, we put this term as it is. This term as it is, because this is obtained by combining the mixed order partial derivatives. This term we put as it is. Change here. And the term that we have combined, okay, the term that we have combined gives me nf, okay, which is this. So this term will give me this one. And on the right hand side, you get n square f. Okay. Now we can take this nf to the other side to write the right hand side as n into n minus 1 f. Okay, so when you bring nf to the right hand side, you get n into n minus 1 into f. Okay, so this gives me this final result which we wanted to prove. Okay, so this gives the proof of the second expression, this equation 7. All right. So if these assumptions are satisfied, what are those assumptions? Function is homogeneous. First and second order partial derivatives are continuous. Then these two results will hold. Okay, so before applying Euler's theorem, you should check these assumptions are satisfied. If these assumptions are not satisfied, then you cannot apply Euler's theorem. Okay. So this completes the proof of the Euler's theorem. Now let us go to some example. So let us consider this function. fxy is equal to y raised to 3 minus x raised to 3 divided by y square plus x square. This function, the domain of this function is R2 minus 0, 0, because if x and y both are 0, then the function will lead to a 0, 0 form and the function is not defined. So we exclude 0, 0 from the domain of the function. At other points, that means the points other than 0, 0, this function is well defined. Okay. So first of all, we will verify the conditions of the Euler's theorem. So what is the first condition? The function should be homogeneous. For homogeneity, we have just seen how to check the homogeneity of the function. So here you can check that the function is this is a homogeneous function of degree 1, and then you calculate the partial derivatives to check the partial derivatives are continuous. So we can calculate the first order partial derivatives, both first order partial derivatives, and you can also calculate the second order partial derivatives. Okay, so this calculation I am skipping because you already know how to calculate partial derivative. But I'll repeat it again. When you calculate the partial derivative with respect to x, you treat y as constant and differentiate this as if it is a function of just one variable x. When you calculate partial derivative with respect to y, you treat the function f as a function of x as a function of y only, and variable x will be treated as constant. Okay, and then you do this normal usual derivative. Once you have this partial derivatives, the first order partial derivatives, once you have this first order partial derivatives, this is the partial derivative with respect to x, you can differentiate this function again with respect to the variable x by treating y as constant. Okay, when you do this, you get this second order partial derivative with respect to x. So after simplification, you will get this one. Similarly, you have the partial derivative of f with respect to y is this one. When you differentiate this with respect to y, you get the second order partial derivative, which comes out to be this. Okay. And for the mixed order partial derivatives, for example, if you want to calculate this one, so here the derivative, the first derivative is obtained with respect to x. So that we already have. With respect to x, we have this first order partial derivative. So you differentiate this function. Differentiate this with respect to the variable y. Okay, so you will get this mixed order partial derivative. Differentiate with respect to variable y by keeping x as constant. Okay, so after simplification, you will get this one. And for this, we see that the first derivative is with respect to the variable y. So first derivative is with respect to variable y, which is this one. So when you differentiate this function with respect to the variable x by treating y as constant, so you will get this one. You will get this second order, and then after simplification, you will get this. Is there any more simplification? After simplification, your final answer will be this. Okay. So from here, one can easily check that the first order partial derivatives and all the second order partial derivatives are continuous. Therefore, one can apply the Euler's theorem. And when you apply the Euler's theorem, you need to know the degree of the homogeneous function. So this is a homogeneous function of degree n, where n is equal to 1, that we have just calculated. Okay. So one can easily check that substituting these partial derivatives, when you substitute all these partial derivatives in this equation, you can easily substitute the partial derivatives here. We have all these partial derivatives, and you can check that can calculate this relation, this left hand side, and you can show that this left hand side will come out to be the value of the function. And similarly, you can check that when you substitute the second order partial derivatives on the left hand side, this will come out to be 0, and which is equal to n minus 1 into f. In our case, for this example, the value of n is 1. Okay, so this is equal to 0. Okay, so this is just basic elementary calculations so we have to apply. So this is how you can check, verify the Euler's theorem for homogeneous function. Okay, similarly, you have another example. This is so you have to show that this relationship holds. Okay, so for this, what we do is we define the function of xy as sine u. And see that u is given to be sine inverse x plus y divided by root under x plus root under y. Okay, so you can define the function xy, the function of xy, the function f of xy as sine u, and sine u means this is x plus y divided by root under x plus root under y. Now this is clearly a homogeneous function of degree 1 by 2. Therefore, by using the Euler's theorem, I get this relationship. Okay. Now you can you can apply the chain rule. You can apply this chain rule here. So df by dx will be equal to, you can see that fxy is a function of u and u is a function of xy. Okay, so you can differentiate f with respect to u and then u with respect to x. So you get this one. And similarly, the second term, this df by the partial derivative of f with respect to y can be written in this form. Okay. Now, when you differentiate f with respect to u, f is sine u. So f is sine u. We have said this in the beginning. F is sine u. Derivative of sine u will be cos u, right? So this quantity del f by del u will be cos u, and del u by del x will be del u by del x, right? So this will be equal to cos u, and this will be del u by del u. Okay, so from here to here we go using this derivative of f, and then we can take this cos u to the right side, to the right side. So we get tan of u. So we get this relationship. Okay, this equation 10. Now we differentiate equation 10 with respect to x. You get this one, and differentiate 10 with respect to y. You get this one. Okay, you can check these derivatives. I'm not going to into detail how these derivatives are calculated. You know already how to calculate the derivative. So derivative of equation 10 with respect to the variable x will give me this equation 11, and derivative of equation 10 with respect to the variable y will give me equation 12. Now we multiply equation 11 by x and 12 by y and add them together. So you have x squared, second derivative, x first derivative, xy mixed derivative, and another xy will combine these two. So you have 2 times xy mixed derivative. Then here you have second equation is multiplied by equation 12 is multiplied by y. So this will give you y first derivative, then y squared second derivative here, right? So left hand side is exhausted, right hand side we will have x into, you can take 1 by sec square u outside, so you have x into del u and y into this first derivative. Okay, so after this you get this equation, and now we can use equation 10. Can use equation 10. Okay, and
Sir, if
here,
in equation 10 tan of u tends to infinity, then
no, 10 of you not going to infinity.
sir, why?
Why will it go?
Because sine inverse varies from -1 to 1.
Yeah, so cos u can be tending to 0, no, for some value of xy. So
Yeah,
tan
so
u.
those values are not considered, only for finite case.
Okay,
Okay,
so only finite cases.
yeah. So if there are
Okay.
certain values where you blow to infinity, those values are not considered.
Yes, sir.
Okay, so use equation 10 here, so you get the last equation which we wanted to prove. Fine. Okay, and now we have some homework. You can try these questions at home on Euler's theorem. And there are more questions on Euler's theorem in the assignment sheet that also you can try. So that completes Euler's theorem. Any question on Euler's theorem?
Sir, in the previous example,
Hmm.
so how do we know that the double derivative of u is continuous partial derivative?
You can see that the numerator is a polynomial. Let's say
Sorry,
consider
sir, I
that
didn't hear that.
this is a polynomial.
Yes, sir.
Polynomial is always continuous, and this is also a polynomial.
No, sir, example 2.
In example 2, you can calculate the double derivative, it will come out to be continuous.
So in 11th and 12th equation, we did this step.
And then because you see, from the structure itself, it is very clear. This is a very regular function. You can differentiate this often, I mean, as many times as you like. And this is
Okay.
also a very regular function, root under x plus root under y. Right. And sine is
Yes,
also a
sir.
very regular function. Sine can be differentiated as many times. You differentiate sine, you get cos. You can differentiate cos, you get sine. Because as many times you can differentiate sine. So this composition will also be differentiable. So from there you can easily see that these are all well-behaved functions, very regular functions. We only require the functions to be twice differentiable partially. Okay, and those are continuous. But this has infinite derivatives. Okay, but if you
Sir,
really want to go into more detail, like checking the differentiability, checking the partial derivative continuity, second order partial derivative continuity, you can find the partial derivatives explicitly and then apply epsilon and delta definition to check everything. But it's better to use the properties of the continuous functions. Like if you have two continuous functions, then the sum of the continuous function is continuous, product of continuous is continuous, division of two continuous function is continuous. All those properties you can use it here.
Okay, sir.
Okay.
Yes, sir.
sir,
Yeah.
can you give one insight about how Euler thought of this? Like, what is the relation in the future of this?
This is just a kind of special result for uh, for homogeneous function. So
Any link in the future of this?
future means what?
How it is creating a connection?
Sir, how is related to physics? It is related to physics.
And
Physical
also,
physical application. Somebody who is working in physics can tell. Because I'm a mathematician, so I'm not aware of physical applications like how this can be used in physics or in some other branches. Okay.
okay, okay, sir.
Okay, sir. And sir, Euler theorem is proved only by homogeneous functions,
Yes.
right?
Yes.
Okay, sir.
We have used in the proof the proper definition of homogeneity. Okay. So it is only for homogeneous function. Now let us come to this chain rule.
So I just had one question.
Hmm.
Sir, in questions related,
I cannot hear you.
in sir, in questions related to Euler's theorem in exams, we don't always have to prove the continuity of double derivatives, right?
No, don't prove. Just see at intuitive level using the properties that I just mentioned.
Okay, sir.
Most of the times you are dealing with polynomial, sine, cos, exponential. These are all very regular functions. Exponential you can differentiate infinite times. Sine you can differentiate infinite times. Polynomial you can differentiate infinite times. Okay. So some combinations
Yes,
of
sir.
exponential, some combination of sine, cos, ratio. So from there you can guess these functions are partial derivatives of these functions will exist and will be continuous.
Yes, sir.
Okay. So if you start proving the continuity of these partial derivatives, it will consume a lot of time. So don't do that. But if you want to mention like something like some properties using these properties, or polynomial function is continuous, sine is continuous, differentiable, so those properties you can mention to claim that the assumptions are satisfied. Okay, so now let us go to this chain rule. So consider a function of two variables x and y, and let us assume that x is itself a function of another variable t, and y is also a function of another variable t. Then we can say that so you have f x y can be written as f. X is a function of t, so you can write instead of x phi t and xi t. Okay, then the derivative of you can say that this is z. The derivative of f or z with respect to t. So basically you can say that this is now a function of t and denote this by z. So derivative of z with respect to t is equal to the partial derivative of x, partial derivative of f with respect to x into derivative of x with respect to t, plus partial derivative of f with respect to y into derivative of y with respect to t. Okay, this is the chain rule. Now the proof of the chain rule is very simple. I'll quickly go through this. So we see that f is a function of x and y, and x and y both are function of a variable t. Okay, so what we do is we change the value of t from t to delta t. Okay, so when t is changed from t to delta t, x will also change. So x will, let's say x will change from x to delta x, and y will change from y to delta y, because x and y are function of t. So when you make delta t, when you change t by delta t, then x will, let's say, change by delta x, and y is changed by delta y. Okay. And when x and y are changed, then z will also change. Z is f phi t xi t. So change in z is denoted by delta z. Okay. Now we are given that the partial derivatives are continuous and f is differentiable. So that means the change in f, since f is differentiable, so using the definition of the differentiability, change in f can be written in this form, where epsilon 1 and epsilon 2 both goes to 0 when delta x delta y goes to 0. Okay, using the f is differentiable, so using the definition of differentiability, just recall the definition of differentiability, you can write the change in f in this form. Okay, and then you divide both the sides. You divide both the sides by delta t. Okay, so change in f is basically change in z, because f, another notation for f is z. Okay, so delta z is equal to delta f. So, and yeah, as I said, this step is because of the differentiability of f, using the definition of differentiability. And then you divide this equation by divide this equation by delta t, both sides, and take limit delta t goes to 0. So left hand side will be delta z by delta t, and limit delta t goes to 0. Right hand side will be df by dx, del f by del x. This does not depend on t. Okay, so you can take this out of the limit. This is just a constant. So you get this term, and this will give you this term. This will give you this term. This will give you this term. Okay. Now when you take the limit, what happens then? When you take the limit, this becomes derivative of z with respect to t. Okay. So basically you get this quantity. How about this one? This one will become this, because the limit delta t goes to 0, delta x by delta t will be derivative of x with respect to t. Okay. Similarly, this will become derivative of y with respect to t. So the second term will become this one. Okay. And this term will be 0 because epsilon 1 goes to 0 when delta x delta y goes to 0, and delta x delta t, when delta t goes to 0, is the derivative of x with respect to t, which is a finite number. Okay, so this term will be 0 because of this, and similarly this term will be 0. So you get this one. Okay, so this proves this chain rule. Yeah.
Can you please again explain why epsilon?
Sorry? Can you speak a little bit louder? I think I'm finished now because time is already over. So, but the proof we have completed the proof. If you have any question, you can ask me.
Sir, can you please again explain why epsilon 1 del x by del t is equal to 0?
Okay. This quantity. This can be written as into two parts. Delta t goes to 0, epsilon 1, limit delta t goes to 0, delta x delta t. Right? This term is dx by dt, which is a finite number because x is a differentiable function. Okay, we have already said in the assumption x and y are differentiable function. T. Now this quantity delta t, limit delta t goes to 0, epsilon 1 goes to this quantity goes to 0. Why it is so? Because if delta t goes to 0, delta x will go to 0. Why? Because x is a continuous function of t, and similarly delta y will go to 0. Y is a continuous function of t, so when delta t goes to 0, delta y will also go to 0. Okay, so this limit can be written as limit, instead of delta t going to 0, I can say that delta x delta y goes to 0 0 of epsilon 1. Okay, and epsilon 1 goes to 0 because of this, because f is differentiable. So from the definition, in the definition of differentiability, this will go to 0. So you get 0. Okay. So basically, you have 0 into a finite number, delta dx by dt, which is 0. Is it clear?
Okay, sir.
Yeah. Any more question?
States that if the partial derivatives are continuous, then f is differentiable. So, sir, that proof involved mean value theorem. So, is that proof in relevant for MT, or we can leave it?
You can leave the proof, but I have included this. I have discussed this in class because sometimes students learn the proof also.
Yeah.
Proof is not relevant for your MT examination. Okay.
Yes, sir.
Any more question? So if no more question, then we can stop the session and I'll see you tomorrow.
Hello.
Sir is just moving to his office, like he was there, so he'll be back soon.
Thanks, Arav.
Hello. Yeah, just a second. Give me a second. Okay, sorry. Yeah, now I'm online. I'll share the screen and start the class. Sorry about it. Okay. Okay. Let me share the screen. Okay, that's what. So we were discussing about the. I'll just briefly cover the. Kind of outline whatever I taught last time. So we are basically discussing about the superconductivity, and superconductivity primarily is a phenomena which is different from a very good conduct. Okay, let me ask you. Can you hear me?
Yes, sir.
Yes,
Yes,
sir.
sir.
You are able to see whatever I'm showing, right?
Yes, sir.
Okay, good. Great. So yeah, so it's not just a simple better conductor or an ideal conductor. It's different from an ideal conductor. In a way, it's something different. Of course, we'll see. I mean, let me just go to. It's like a super, as we discussed last time. So it has the property that below a certain temperature, which we call it a critical temperature, the resistivity or resistance goes to absolutely zero. And this is one of the two important properties of superconductors, which you can define. So it passes through, like, there are no vibrations as such. There are no vibrations of the background atoms or ions through which the electrons can get scattering. So it passes through, like, there is no scattering, and important thing is, without any voltage drop, the current can be sustainable, and then it can keep flowing for very long time. So this was just simply the background. Kamali discovered it. We discussed these things in detail last time. So okay, that was like how was it discovered and how to measure it, how to confirm that it's really zero. You cannot simply check it by simply a voltmeter, because voltmeter would have a certain sensitivity below which you cannot measure. The same thing happened even for the chameleons. He could not measure below micro ohms, so it was like going from like 1 to the power minus 1 ohms to 10 to the power minus micro ohm. So he used a kind of a different way technique to really confirm that the resistance is really zero through this thing. So there are two properties. One is zero resistance, and another one is this that superconductors expel the magnetic field from inside it, and it's not simply by like Faraday's law through which you can explain it. Actually, it's completely different in a way that even if you do not apply the magnetic field, there is no del B by del T, so the magnetic field does not change as a function of time. Even if you apply the magnetic field in normal state and then cool it down, And in that process, since magnetic field is not changing, so magnetic field should remain inside the superconductor. But actually what happens that even in that case, the magnetic field gets expelled. So this is not a normal electrodynamics. So it defies the normal laws of the electrical conductivity. It also defies the law of electrodynamics. Okay, so it's something else. That's why we call it superconductor, not an ideal conductor, because even if you apply the magnetic field in normal state and then cool it down to a superconducting state, still the magnetic field gets expelled from inside it. So which is against the Faraday's law. So that itself, the effect is called Meissner effect. It's not a normal simple. That's why we do not call an ideal conductor. This is something else. This is called, that's why we call it superconductor. And that's, we also discussed this if you keep increasing the magnetic field, of course it expels the magnetic field, but above a certain value of magnetic field in type 1 superconductor, it becomes normal. It comes into the normal state above a certain field, which is called critical field. So it has two properties. One is related to, as it has two important properties, that the transition, the resistivity is 0 below a certain temperature called critical temperature. In the same way, below a certain magnetic field, it remains in superconducting state, that is called critical field. And in the superconducting state, the resistance is 0 and the magnetic field inside the superconductor is 0 in the type 1 superconductor. Type 2 superconductors are such that there are two critical fields. One is HC1 and we call it HC2. Between HC1 and below HC1, it's pure superconducting state. Magnetic field cannot penetrate inside the superconductor, but above HC1, it remains superconducting, but magnetic field can penetrate inside the superconductor, but in a certain way, and in a quantization of a particular value of flux, which we call it this 2.07 into 10 to the power minus 7 Gauss centimeter square. It has to have, like, it flows kind of a vortex.
It's 1630.
Okay, and through which it passes. So those parts through which the magnetic field can pass, that becomes normal state, but other parts remain superconducting. So it's kind of a mixed state. That's what it's essentially called mixed state. And if you go above critical field to HC2 value, it becomes normal conductor. It goes into the normal state. So these are kind of essential properties of the superconductor. And as I said, for a long time, the theory or theoretically, this superconducting phenomenon could not be explained because it was discovered in 1911. Till 1956, there was no explanation as such about the superconductor. I mean, it was so absurd that it was not really kind of explained. But in 1956, Bardeen, Cooper, and Schiffer, Bardeen is the one also was responsible for the discovery of the transistor, actually. So he actually received Nobel Prize twice. For that, this is called Bardeen B, Cooper C, and Schiffer S. So BCS theory of superconductivity. So there is a way to explain it, that electrons get bound into pairs with an opposite spin and opposite momentum via electron-phonon, something called electron-phonon interaction. Phonons are nothing but quantized form of the vibrational waves of the background atom. Okay, and these pairs are called Cooper pairs, and they are in phase with each other. So it's a and then they more and more electrons start to form the Cooper pairs, and they come kind of in a phase with each other. So there is a macroscopic phase associated with this superconducting condensate. That's what it is called, superconducting condensate, when all these electrons gets condensed into the Cooper pairs. So they get a single phase. It's like, you can observe the interference phenomena and so on with this superconductivity phenomena at a macroscopic scale. And length scales could be even in some superconductors could be very, very large. I mean, hundreds of microns and even larger than that, the coherence length. And this is the only phenomena through which a practical form of quantum computer has been realized so far. I mean, there are different concepts about the quantum computers, but so far, the quantum qubit has been realized via superconducting. I mean, the only quantum qubit is basically a superconducting qubit made out of the superconducting materials. Different materials, as we discussed, different elements. Most of the elements become superconducting either at ambient conditions, that means ambient pressure, sorry. Usually the TC is very low, and the alloys, some of the alloys would have higher critical temperature, something in the range of 20 to 25 Kelvin. And that's where the BCS superconductivity theory could put a limit for the highest TC that was around 20 of the order of 25 Kelvin. By 1970s, 80s, it was quite realized that was confirmed via BCS theory that the TC cannot go above 25 Kelvin. So it was like more or less things were known. Only research was going on to get more and more alloys, superconductors, having higher, I mean, TC 25 Kelvin, but higher HC critical field also, because that would have direct applications in the high field magnets. So this is essential. It's still most of the, I mean, widely accepted application is high field magnet. Usually, most of these MRI machines would use are still using superconductors. So this is the chart. I think you can still get this chart also online. So these blue ones are at ambient pressure, and green ones become superconducting at under higher pressure only, the element, and rest remains non-superconducting. So you can see that the materials with higher conductivity like silver, gold, they do not become superconducting even at higher pressure. Similarly, this magnetic elements like cobalt, nickel, iron, of course, becomes superconducting, but still at high pressure, they do not become superconducting. So these were the rules. That's what Matthias applied these rules, that materials should have high symmetry, high density of states. Oxides would not be superconducting. Magnetic materials would not be superconducting. Stay away from the insulator, and that's how you can find a new superconductor when the search for the superconductivity was going on within the different alloys materials. Okay, there was 6th rule, that stay away from the theoretician. It was kind of a joke because it was known that still it's actually true that you cannot predict theoretically. You cannot predict superconductivity theoretically. You cannot explain, okay, this material was going to be superconductivity, or this would be the TC of that. And still, I think it's true. So these were the two scientists which kind of defied all the rules of the friend Matthias, and they discovered a superconductivity in a new material, actually in the oxides, which was primarily also magnetic in parent state. All these 5 rules were kind of defied, and that was till 1980s. Mostly this like how the TC was increasing as a function of years. So by 1980s, we had only superconductors with a TC of roughly around 25 Kelvin. And all of a sudden, this Carl X. Mueller and Bernoulli discovered a superconductivity in this lanthanum barium copper oxide, which is an oxide material. And if you take parent they doped or substituted lanthanum with the barium to certain extent. So parent compound lanthanum copper oxide LaCuO4 is an antiferromagnetic material. So they doped it. Of course, magnetism was gone, which is still actually that rule is true. So lanthanum barium copper oxide was non-magnetic, but it's oxide, and parent since lanthanum copper oxides LaCuO4 was magnetic. No one expected that it could be a superconductor. So they worked on it and they found that the TC is around 34, 38 Kelvin and so on. Which was a quite, drastic change in a way, because BCS theory predicted that TC cannot go above 25 Kelvin. So they discovered a material which was kind of defying the prediction of the BCS theory. And it was so, the effect was so much, it was so impactful that within a year they received Nobel Prize for this discovery. And very soon, within a year, some similar kind of compounds were discovered having the TC more than the 77 Kelvin, like this yttrium barium copper 07, which is called 123 material, having a TC of 91 Kelvin. Then this bismuth, calcium, strontium, copper oxide, and so on. So this family usually is called as a cuprate family, because essential feature is this copper oxide planes, two-dimensional copper oxide planes within the system, which is an essential feature of all these oxide superconductors. So they are called cuprates, and the maximum is around 135, 136 Kelvin, having this HgBa calcium copper oxide superconductor. So within 1 or 2 years, it was like the TC was kind of increasing, and at that time it was there was so much of hype that soon we will realize a room temperature superconductor. A lot of funding came in, and there was a lot of research, but these materials are still interesting, and as I said, they received the Nobel Prize for that. Still, we do not know how the superconductivity occurs, because this BC theory cannot be applied to these superconductors. We still do not know how the superconductivity occurs. We do not know theoretically what is the mechanism. Of course, copper pairs are there, essential features are there, they become zero, they get zero resistivity, they have the Meissner effect and everything like other superconductors. But BCS theory cannot be applied to these superconductors, which we right now know. But we also do not know what essentially leads to the formation of Cooper pairs in these cuprate materials. Now, there are other superconductors also, which I have not included in this lecture. There are also something called nictide superconductors, iron arsenide based superconductors, which were discovered around 2006-7. Highest TC, as far as I remember correctly, is around 55 to 60 Kelvin. So the TC is not that much high. And then there was a recent, there are some discoveries in the where the TC is close to 300 Kelvin, but you have to apply very, very high pressure actually. And then there was a very interesting discovery, I think 3-4 years ago from Bangalore, IIC Bangalore. They said they have discovered the room temperature superconductor in gold and iron alloys. So there were some nanoclusters of gold and iron, and in which they said they have discovered the superconductivity. But still, it is not conclusive. I think they have not provided probably the sufficient. It's not really accepted yet that whether it's a superconductivity or not. That is still controversial. So this is kind of a background of the superconductivity in such a way with some essential features. So as I said, there are two essential features of the superconductivity. This is an actual experimental result of this yttrium barium copper oxide 100 nanometer thick film. having the TC of, let's say, like 90 Kelvin, below which it becomes superconducting. And another feature is that above TC, the magnetic field can penetrate through the superconductors, but below critical temperature, a magnetic field gets expelled within the superconductivity. So they do not like each other. It's like there is a kind of magnetic field and superconductivity. It's not compatible with each other. That's what you can think. That's why most of these magnetic materials are not superconducting. So this YBCO, or this cuprate superconductor, which are also called cuprate high temperature superconductor. High temperature, why? Because these are different from this BCS type of superconductors, which limits the TC to be around 25 Kelvin, and they have higher TC like 90 Kelvin, 100 Kelvin. Also, still it's a low temperature compared to the room temperature, but high temperature in comparison to the BCS superconductors. That's what the nomenclature comes from, because this has TC of around 25 Kelvin at the BCS, and most of these cuprate superconductors have TC of the range of like 100 Kelvin, 120, 135 Kelvin, and so on. And with pressure, that TC can be increased up to, like, say, I think 156 or 7 Kelvin, something like that. So what essentially is a feature, most of these superconductors have this copper oxide planes, which is written over here, that CuO planes. Copper is, like, say, this red atoms, and oxygen are this oxygen atoms sitting in this plane, and they make this planes. And you can imagine this to be extended in X, Y, and Z direction. This is something called this is a unit cell of the crystal of a superconductor. So you can think this is one unit cell, and then if you keep repeating in all three directions, you can make a crystal of the YBCU superconductor: yttrium, barium 2, copper 307, and that's what we call it 123 superconductor. So these chains are, these planes are extended through the in X. Let's say if we assume this to be XY plane, so within the XY plane they have this copper oxide planes, CuO2 planes actually. And then along the Z-axis they have these chains, because this one of two oxygen atoms are missing within that plane, so they form a chain. So this copper oxide chains are actually used to dope this copper oxide planes. So as you increase the number of oxygens along this Z-axis, this would start to take the electrons from the copper oxide planes, and the copper oxide plane would be doped. In some other superconductors, it is done by the putting like lanthanum versus barium, because lanthanum is 3+, barium is 2+. So by this way you can dope it, but in this YBCO it is done by this O7, putting some extra oxygen. If you have O6, then this atoms in the oxygen atoms in the along the Z-axis, they are not there. So it's basically doping is 0, undoped part, and it is an antiferromagnetic material. As soon as you start to dope, that means you start to put more and more oxygen into this along the Z direction. Then you start to dope the copper oxide planes, and superconductivity starts to appear. Something like, I think, 0.15 holes per CuO2 planes, and the maximum TC occurs at something like 0.25, and then again it starts to decrease. And there are certain, this is something called phase diagram of the usually about the copper pair, something called underdoped, optimally doped, and overdoped. So underdoped also has some features like something called pseudo gap, which I will not discuss here. Then it's not a normal, like a metal, this in the normal state, not a normal metal. Of course, in the undoped part, it's an insulator, but when you dope this copper oxide planes, it becomes metallic. As we can see that as temperature decreases, resistance also decreases. And the highest TC occurs at 90 Kelvin, at which we know that it's roughly 0.07. It goes to the transition from non-Fermi, because, and it's linear. That also, it's an indication that the overall metallic part is not a normal, like a Fermi liquid like behavior from this kind of a linearity of the resistance versus temperature part over there, because we know that normal metals are not really for normal metals, the resistance is not really linear as a function of temperature. So this is an actual YBCO thick film. Okay. Another, as I said, this superconductivity and magnetism, they do not go, all together, because it's like they have the antagonistic kind of a relation with each other. They do not like each other. So if you use some kind of a magnetic materials, one of the interesting magnetic material with a similar kind of a phase diagram is called something called manganites. Okay, I will not go into the details because it requires a lot of background information. But what I will tell you that these materials undergoes from a paramagnetic to ferromagnetic. They becomes ferromagnetic, something like around 250 Kelvin. One of the member of this family. And at the same time, they also becomes from insulating to metal. And if you apply the magnetic field, this transition temperature keeps increasing and resistance also gets decreased. So there is a very large magnetoresistance, negative actually magnetoresistance associated with these compounds around the transition temperature. And that's why these materials are also called colossal magnetoresistance, very large magnetoresistance. They might have applications also. They are also similar kind of material like this high temperature superconductors, similar structure. So that means you can, if you use the artificial way of the growth to make the fabrication in thin film form, you can combine them and see what happens. So you can make a material with the alternating stack of this cuprate superconductor as well as this manganites. Because their structure is same, so you can grow them artificially on top of each other. Okay. So this is possible, as you can see from this kind of this is a transmission electron microscopy picture. This is a substrate, something called STO, which has also the similar lattice parameter as for the YBCO or LCMO. YBCO is the superconductor, and LCMO is the manganite material. So you can see this unit cells of the YBCO. This is large because along C-axis it has like 11.6 angstrom, and LCMO has lattice constant along C-axis is about 3.87 angstrom. So you can see that this is a large unit cell, which you can see directly over here. Whereas the in-plane lattice constant is almost same for both the materials, which is around 3.9 angstroms. So you can grow artificially these layers, YBCO, LCMO, and so on, superconducting and ferromagnetic. And then you can try to see what happens in this case. So there are different kinds of phenomena which could be observed in this system. What we can also observe that there is a large magnetoresistance, which we call it a kind of giant magnetoresistance, when it goes into the superconducting state only. Then only this kind of a superconducting state is observed, and this only observed when these two LCMO, this is a tri-layer, not multi-layer, like you start with LCMO, YBCO, and LCMO. So when this magnetization of LCMO, both the LCMO layers are anti-parallel to each other, then you see a large magnetoresistance. And in this figure, let's say figure 1A, you can see that the magnetoresistance around this figure 0, this keeps increasing over there and goes away when it is in the normal state over there. But this occurs only, this magnetoresistance occurs when it's close to the transition temperature over there. This is something called photodoping effect. In this, like light does not have that much of impact on the single YBCO film, which is like the graph on the B. It's a slightly underdoped film. That's why the transition temperature is lower. But if you put the light, which is like a small black line, when you put the light, solid line over there, then the change in the transition temperature is very small over there. It does not change that much. But when you have a bilayer, that means two layers, one layer or 12 unit cells of this YBCO and 40 unit cells of LCMO, actually the change in the TC is too large, like approximately like 30 Kelvin and so. So there are some unusual effects which can be, which we cannot even predict that's going to happen, which happens in this kind of a multi-layers. We also see certain kind of an effect like this magnetization of LCMO as we go into the superconducting state starts to modulate in one layer. If you have like a multi-layer, 10 layers of YBC or 10 layers of LCMO, and you magnetize it, and then you go into the lower than the superconducting temperature, then in one layer this magnetization starts to decrease, and another layer starts to increase. So there is kind of a modulation of this LCM. So there is an effect, not only the magnetism effect. What is the essential takeaway from this slide? That not in usually it was known that superconductivity is affected by the magnetism, but here what we see is that magnetism also can get affected by the superconductivity. How do we make these films? How do we grow this kind of artificial layer? One way is something called this pulse laser deposition technique. What you have is something called target. So you take a polycrystalline target, you make essentially a YBCO thick kind of a palette, and then you put a laser pulse on this target. Very high intense laser pulse, which you focus it in a small spot size. So most of the energy is concentrated on a very small spot size. So the electric field of the laser pulse is very, very high. And due to that electric field, the breakdown occurs in this polycrystalline palette. And due to this dielectric background, electrons go away, and rest of the remaining part is the background ions of the sitting ions in the solid. And as these electrons start to follow the electric field of the laser pulse, it starts to get collision with the background atoms, and this whole crystal gets all the bonds starts to break, and these atoms or ions comes into the vaporized form, and they form a plasma. Plasma is essentially nothing but a mixture of the neutral atoms, ions, electrons, and this is something called plasma plume. That's what it is coming after that. And if you have a low pressure inside there is a chamber, something like this, which you can see on the right bottom. If there is a vacuum inside it, once this plasma plume is formed, it starts to kind of expand. And if you place your substrate over which you want to grow your material, this plume will reach to this substrate, and this will start to grow in a crystalline form, like in a single crystal way over the substrate. So there are certain advantages of this pulse laser deposition compared to other growth technique, because these high temperature superconductors or these manganite materials have lot of elements. So for a single element, a material having single or binary kind of an alloy, that is still easier to grow with different other techniques. But pulse laser deposition can transfer the same structure, but because you want to transfer the stoichiometry also from your target to the substrate, like yttrium having one element, one atom, barium 2, copper 3O7. So in that way, usually it's very difficult for other techniques. This technique is quite successful in a way to transfer the stoichiometry of the target to the substrate. So this whole film can be all stoichiometry with the same crystal structure can be transferred. Okay, I don't want to show it. And what you essentially can do is also you can using something called electron diffraction. You can grow it layer by layer, like one unit cell is formed, then second unit cell. Then you can always control where do you want to stop it. So this is an electron diffraction spots on a camera. You take an electron gun from the surface, it gets diffracted. And then you see these are something called diffraction spots. You will study about the X-ray diffraction or electron diffraction later on in the various courses. So this gives you the symmetry of the atoms of your surface. So directly this spacing between these spots is related to the interatomic distances actually. So you can calculate, what is the interatomic distances, or what is the symmetry, whether the your atoms are sitting on a square lattice or a rectangular lattice or hexagonal lattice. By the symmetry you can find it out, and also by the spacing between them you can find out the atomic spacing also between your on the surface of your material. So if you start to observe the intensity as a function of time as it grows, you can see on the right hand side of the bottom of the screen, like say figure B, the intensity goes down and then comes up, goes down, comes back up. So between the two maximas, actually one unit cell is formed over there. So you can in situ monitor the thickness, you can in situ monitor the roughness, you can in situ control actually the growth, whether you want to grow 3 unit cells, 4 unit cells, 3 layers, 4 layers, 5 layers. So that's what all these things can be measured over here. Also in this electron diffraction phenomena. Similarly, like now you can grow the other layer. So that's what we grew, this YBCO LCMO 10 nanometer into 10 times by layer, and this acts from the X-ray diffraction or neutron reflectivity. You can find out the information, the thickness, bilayer thickness, whether the bilayer has formed or not, what is the individual thickness. All this information could be we could also get, and then we can of course do the resistivity measurement, and then you can see that we can easily get this relation. So you can see that these are nicely grown YBCO and LCMO films, and up to the large scales over there. So these are kind of artificial lattices which you can grow of different thicknesses. YBCO, 1 unit cell given by this red rectangular kind of box on this, and these are like chains over there, which I was talking about, this marked by the arrows. These are the chains over there, and this is the LCMO film. So these are all atoms, different atoms, which you can see this contrast in the black and grayish contrast, different atoms, or giving idea from the different Z numbers. So the higher the Z number, higher is the contrast. Just give me a, sorry, I have to take this call. हेलो, हाँ, एक कर रहा हूँ मैं, 1 मिनट करता हूँ कॉल, ठीक है, कर रहा हूँ, हाँ ठीक है। Okay, so yeah, this is the transmission electron microscopy picture. So what we can do is we can grow these
It's 17 hours.
layers of different thicknesses, YBCO, LCMO, like 13 unit cell. But what we observed also, that at the boundary we do not have the chains at the interfaces of this YBCO LCMO. It grows in the between. Let's say we grow 2 unit cells of YBCO, then there would be only one chain. If you try to grow only 1 unit cell, there would not be any chain, and chains are responsible for the doping. So that means that it's not possible to grow one a unit cell. It's not possible to get superconductivity within the YBC 1 unit cell of YBCO. Whether then in 2 unit cells it should be possible. So that's what we did, and we could find out that okay, with YBC 4 layer of YBCO, it's superconducting. 3 layers, of course, superconducting. 2 layers are also superconducting, but with 1 layer it's not really superconducting. So this was all about this presentation. What now I can show you some, let me see if I can show you a movie also about this superconductivity phenomena. You would probably like it. Just let me check presentation. Just wait a second. Let me try to find out the movie. Wait a second. Wait a second. Um, just give me a second. There's some issue with the. Meanwhile, I start another movie for you, and you can probably look into that. Meanwhile, I will try to fix it if. Presentation. Okay, so let me start sharing the screen. So I think you can see it. What essentially it is like a flash dance, which is also available on YouTube. It shows how the like Cooper pairs are formed, and through this flash dance, and how do they move, and as temperature decreases, as they start to form, how the superconductivity is created, and how do they behave through this just wait a second. Yeah, so that's what it gives a kind of a feeling. I think you can also see. Meanwhile, I tried to look this another documentary if I can kind of fix it. Sorry, I think. Oh, I started to. Maybe I should wait. He's trying to.
Sont des oxydes à base de céramique.
News today in hospitals.
To that. Apart from that, also there are so many books. So any book on communication skills or technical writing will have these topics.
Business correspondence and report writing by R.C. Sharma. That's the one, right?
R.C. Sharma and yeah, Chris Mohan.
Okay, yeah, thank you, sir.
Yeah. So Aditya, can we start now?
Yes, sir.
Yeah, thank you. So good evening all, and wish you all a very happy new year. Let us hope that the year 2022 augurs well for all of us, and we see you soon on campus. Although we had plans to bring you back on campus by this very day, but because of the recent surge in the COVID cases, that has been put on hold. So we'll continue to talk online. But let us hope, because all your seniors have already come, and maybe in a couple of months' time, if things improve, you will also join us physically. So till then, we have to continue like this. So hope is what keeps us going, and we always hope that tomorrow will be better than today. So let us hope that. Okay, so friends, as I said in response to Aditya, the examination pattern is not known till now. It will be clear in a day or two when we have a meeting of all the teachers teaching this course with the coordinator. Most probably it will be objective type. Objective type questions will be taken from the topics that have been discussed till now. I mean, any topic that has been discussed before your midterm examination will be part of midterm examination. So as I said, we started discussing the process of communication, in which we try to understand what do we mean by communication, how is it important in our life, what are the different types of communication, the two broad categories, verbal and non-verbal. Then we also talked about the different barriers to communication, and in that we talked about a range of barriers arising out of different situations, but we had a special mention of barriers of psychology, I mean psychological barriers, cultural barriers, legal barriers, ethical barriers, barriers pertaining to gender, and linguistic barriers. And after that, we talked about non-verbal communication and the part it plays in our professional life. And now we are going to talk about a topic which is called stage fright or stage fear. Well, friends, when we talk about communication, we talk about communication in a professional situation. And professional communication might range from one-to-one communication to group communication to public speaking as well. Now, what happens, and of late, when we talk about online, now online has certainly done a wonderful job in this time and testing times, because of which we have been able to continue our classes. But we'll also realize that, face-to-face communication gives us more exposure and more connectedness with people and more courage to face each other physically. Well, online is giving us another kind of confidence, since we are away from the direct gaze of the people. We are sitting in our own rooms. We have a sense of security. I don't know, false sense of security or true sense of security, but since we have been sitting in our own spaces, in our own homes, and our own settings, we feel emboldened, and sometimes we are able to put across our queries more confidently. But believe me that the world will not be online all the time. You may have to physically present yourself. Now, you might also realize that if somebody is living in the dark for long, when he or she is brought out in the light, he or she is not able to sustain that light. So psychologically, our situation will also be like that. If we continue to talk to people online for longer period of time, maybe we'll be afraid to face them physically. And that is the real worry. Even otherwise, friends, all of us know that standing before people in a formal setting and talking about something which is important and which has some stake is one of the most difficult arts. You will be surprised to know that many of the teachers who have been teaching for years still don't feel confident facing students, although this is our everyday job. I mean, this is our primary job. So, but again, I may be lying if I say that we don't feel nervous before each class. A little bit of nervousness, I won't call it nervousness now, but yes, a little bit of concern, little bit of thinking is always there. Because before we commence a class, we, try to visualize it, try to plan it well in advance so that we make sense. So if I have to talk about stage fear, what will be my examples? How should I begin? What are the points that I would mention? All these things, go on in the making of that moment. So, minded friends, I mean, even the best of us, the most confident speakers also have some moments of nervousness or stage fear, because, we understand that you people belong to a generation of students where you are getting more exposed to such situations where you are allowed to appear on the stage and share your views. So obviously you are better than the generation to which we belong to, because in our days, the schools did not have regular assemblies, or we were never, asked to stand on the podium and, speak something. So it was only once in a while, maybe after 2 years, 3 years, that you will get some chance to expose yourself to such a scenario. And that is why, we belong to a generation which is mostly shy. But nowadays, with better exposure, the children are better exposed. The schools are providing you a lot of such opportunities where you can share your thoughts. And then you are also exposing yourself through technology and through other means as well. But nonetheless, the fear psychosis is something which is natural. If you are not nervous, there is something wrong with you. So people always say that, if you are not making mistakes, you are not human. Either you are subhuman or superhuman, but you are certainly not human. So it is human tendency that the moment we are asked to make an important presentation or stage appearance, even if we have been doing it for years, still we have some moments of jitteriness or nervousness. So friends, we'll be talking about this situation because you may be required to give presentations, you may be required to appear before interview boards, or you may have to interact with important people on important issues. You may be sharing your thoughts or making presentations regarding your plans or your understanding of a subject matter or a business plan, where a lot of stake will be there, because there will be people who will approve of your ideas and they will fund your project. So unless and until you look convincing, you are able to, present yourself in the best possible manner, you are articulate, you are intelligible, well, you will not be able to make an impression and back the contract or the grant for which you have been striving. So that's why this is so important. So I'm just sharing a presentation which talks about stage fright, and we'll try to make sense of it. Well, the human brain is a wonderful thing. It starts working the moment you are born and never stops until you stand up to speak in public. So this is a very humorous, serious comment. Although it looks humorous, but it has serious connotations. And it talks about one of the problems that is called brain freeze. So if suddenly if somebody asks you to stand on a podium and speak on a topic, you have momentary feeling of brain freeze when your brain stops. It stops and you turn blank. You don't know how to begin, how to go ahead. But that moment is just momentary, and then you recollect yourself, recompose yourself, and then you make a move. Fine. So what is stage fear? I mean, it generates from our anxiety or fear, or some of us may have persistent phobia because of our background, because of some unpleasant experiences. So this is realized by everybody, but not in the same measure. Some of us may be having a background in a family where everybody is very outspoken, extrovert, social. If you belong to such a family, you are better exposed and better prepared. On the other hand, if you come from a family of reserved people, where people speak less, people mix up with other people less, there are less visitors, children are not allowed to, share space with their elders or the visitors or the strangers. Obviously, you will develop this kind of a habit in which you will fear going into the public. So, stage fear may be experienced by different people in different manner. And this is really difficult to assess the cause of it for the simple reason, as I said, all of us may have a different makeup, different background, and different experiences in life. So if somebody has experienced some kind of trauma in life, that trauma will be triggered each time such people will be exposed to audience. So their fear will be more compared to somebody who does not have this kind of trauma. So simply put, stage fright is the kind of anxiety, fear, or phobia that we experience while standing on the stage and presenting ourselves. This is also a psychological condition. It is mostly psychological, not physical, because our thinking only causes fear or panic or anxiety. So what happens the more we think about the success and failure of a plan or a presentation, the more conscious we become of it, the more fear or anxiety seeps in. On the other hand, if you take something very lightly, maybe by the time you realize your presentation is over and you are not under any kind of stress. So see, you can just imagine the day of your advanced, JEE advanced. I'm sure all of you may be feeling nervous despite all your preparations for years. All the practice tests, all the Olympiads that you may have attempted by then, on that particular day, even the best of you who ultimately might have turned All India rank 1 may have also experienced the same kind of anxiety and fear. Why? Because this was a big stage for you. You had lot at stake. Fine. So more stake leads to more fear. Fine. So why do we get stage fright? Well, if we biologically look at it, the body is flooded with energy, adrenaline. People say it kept our adrenaline pumping. And this kind of situation arises because of our body response. Fine. So the moment we start thinking more and more, the body or mind alerts the body and alerts all the defense mechanism. And as a result, there is more hormone secretion in the body than usual, resulting in more such unmanageable situations. The second thing, we don't like to be judged. When you are standing in front of people and people are looking at you, and if you find that they are fixed on you, you start feeling awkward, and that also, puts some kind of pressure on your mind, and as a result you feel some kind of shiver down your spine. We don't think our ideas are worth listening to, and partly this happens because of self-deprecating ideas. We always feel low on confidence and belittle our own ideas. We think that, our ideas may be not worth, and so people will not listen to that, or they will not take them seriously. So because of this feeling also, you have that unknown fear of being rejected. And another reason for your stage fright may be your lack of preparation. If you are not prepared for the occasion, you will make inadvertent mistakes, and they will compile your misery. If you are well rehearsed, well prepared, probably you have less fright or less anxiety, because probably you know these steps. And if you have negative past experiences, as I said, the fear of failure is the most dreaded fear in an individual. So supposing you have been unsuccessful in your first attempt, the second attempt will always put more pressure on you. Fine. Because you will believe that it is now or never. If I don't succeed this time, maybe it will be end of my dream, and that will put extra pressure on you. Now, all of us experience these symptoms of stage fright. I mean, there are some visible symptoms, and people sitting in front might easily get to know that, but more than anybody else, you experience these symptoms loud and clear. So you will have hot flushes. Suddenly you will realize I'm having fever, I cannot give presentation. Your heartbeat will double the normal rate, will go up, because of this feeling. You will feel dryness in your mouth. You might feel giddy or might experience headache. You might feel stomach is upset, something is happening. The hands and feet go cold. You're not able to balance your body, so you are going helter-kelter. So, I mean, there is shaking of your legs. I mean, these are all signs and symptoms that you are not your normal self. And coupled with that, there may be some more symptoms, as I said, hot flushes, sweaty palms. The voice quality itself will change. Sometimes you will wonder what happened to your voice, because it will come choking or it will turn hoarse, maybe breaking. So you will also realize that it's not my usual voice. You will feel dizziness, there will be shortness of breath, there will be urge to go to the restroom, although there is no real need. These are all signs and symptoms, of stage fright. Now, I mean, as I said, we are all humans and humans are capable of, thinking. So it does not surprise, it should not surprise anyone if we have a feeling of stage fear. Because, this is a normal process and sometimes it can be used in a positive manner. Because of this experience, you may be pressurized to prepare yourself well the next time you make a presentation. So rather than taking the negatives, you can also take the feedback of your earlier presentation as positive to build upon your failures. I mean, the people who have character, who have guts, people who make something noteworthy in their life, they are all the people who have built their successes on their failures. So if you allow your fear to persist and start making more mistakes or continue to make the same mistakes again and again, you will certainly make your situation worse. But if you take them as positives, as opportunities where you can embolden yourself, prepare yourself well, and overcome the mistakes that you made the last time, obviously your corresponding presentations will be better than the last. So, if you need to overcome your stage fear, you need to build your confidence. You need to organize your notes. You need to have friendliness, impression wise, dedication, empathy, newness, conviction, enthusiasm. I mean, what I mean to say is all you need to do is to have abundance of positivity, abundance of hope, and abundance of, enthusiasm and conviction that you will be able to overcome your limitations. You must try to improvise, then only you can succeed in overcoming the hurdle of stage fear. And how do we do that? It does not happen in a day. We start rehearsing and preparing for that step by step. So if you know how to prepare yourself for the occasion, certainly you will have a better outing the next time. So we say if you have to, make a presentation, you need to know the subject of your presentation. You need to know the audience of your presentation. You need to know the room choreography. Where are you going to present? What kind of room will that be? How large or small? Orientation, the capacity, and then the technological aids that will be available to you. If you can figure it out, probably you don't have to wonder at the last moment, sir, I prepared a PPT presentation, but there is no facility to present it. So how do I do that? No, you already knew that you will be requiring some alternative means because the room does not have PPT facility. Again, sir, I didn't know that it's a huge room. My voice is so feeble, I cannot, address such a large audience without any microphone. Well, if you know, you can make use of that. Fine. So know the room, become familiar with the place in which you will speak. You also need to know the sequence of your presentation. Like whenever we are invited to make a presentation in any professional meeting or conference, seminar, or special lecture, we always ask these questions. Okay, how many people will be there? What is the background of those people? How many speakers will be there in each session? What will be my turn? Will that be first, second, third, or last? What time of the day will that be? Because different time frames require different approaches. If you are speaking to an audience which is barely awakened, obviously you will have a tough time, rather than talking to people in the broad daylight when they are in their senses. Fine. If you are talking to people in the strategic, time frames like just before lunch or just after lunch, again it will be problematic. Like the other day we realized, and we still realize, that this being the last class of the day and you people are dead tired by now, I understand that I have to make extra effort to keep you all awake and interested. So that's why, I may have to maintain extra bit of energy and enthusiasm. Then only it will work. So yes, so knowing the geography of the place really helps, because it makes you familiar and it takes some burden off your mind. So you are required to reach early, walk around the room in which you are going to make presentations so that you familiarize yourself. Stand at the lectern, speak into the microphone, and that we can check. I mean, this is not always possible, but then if it is possible, you are advised to do that. Then you can also look at the audience area and can take stock of how the stage looks from there. And because if you are one of the speakers, you may be sitting in the audience and you may be required to walk from there to the podium. And if you are sitting somewhere in the middle, you may be hitting several people while coming out, and you will cut a sorry figure even before you have started speaking, and that will further dent your confidence. Know the audience. I mean, this is the most important ingredient of any public speaking. Audience. We are afraid of audience, nobody else. So more familiarity with the audience means more success guaranteed. Fine. So know the audience if possible. Greet some of them on arrival. That will ease your pressure, because we all know that it is easier to speak to a group of friends than to a group of strangers. So if you make a couple of friends, you make things easier for you. So if you recall, on the very first day, I made friends with many of you. And now I am much more confident talking to you, because I know I am talking to my friends. And even if I am being judged, I hope I am being judged positively. Fine. So am I right?
Yes, sir.
Yes, sir. Thank you. Thank you. Now, what are the things that bother us? Well, first of all, we bother about how we look standing in front of the people. Am I looking like a genius? Am I looking like a fool? I mean, how am I looking? So our physical look is the first thing. And we always try to make a lasting impression on the audience. So we need to take care of our physical appearance. We need to be dressed to the occasion. We need to take care of our body language. We need to walk professionally with ease and confidence towards the podium. We need to stand there confidently in proper manner without indulging in any oddity of gestures. Fine. Like scratching our nose or tearing our hair or head. And we need to, stand erect and face the crowd. Fine. So if we are capable of doing that, well, the next thing is what are we going to talk about and how are we going to talk about? If we have rehearsed, probably we know how we are going to start. And if we start well, then half of our nervousness is immediately gone. But if in the beginning itself, we put on a wrong slide and we start saying, sorry, I'm so confused. I didn't mean to project this. I wanted to talk about something else. Well, we'll cut a sorry figure and that will spoil our whole presentation. So that's why, friends, before coming to present, you need to make lot of preparation, mental, physical, and of the subject matter. Now, mental preparation requires you to be mentally strong, to visualize the occasion, to leave the occasion. So within your mind, you can just think that I'm standing in front of a podium and talking to 500 people in a large hall. OK, so you visualize that again and again, and that gives you that confidence, that familiarity, that I can do that. Then you visualize that you are sitting somewhere in the middle and you are, walking towards the podium, arranging everything, and then starting with a well-rehearsed speech. So for that, you need to know your material. And the material selection, although we cannot change the topic of our presentation, but we can certainly plan it for the audience. So supposing you are a nanotechnology expert and you are going to address a gathering of people. Now, should you be talking like an expert? Should you be lowering down your speech to a normal speech? Should you bring it to the level of layman? It all depends on your prior research as to who will constitute your audience. So if you find that your audience comprises all the nanotechnology experts and fellow researchers, there is no need for you to lower down your speech. You can continue to use all the scientific jargons related to nanotechnology because you will be understood. But if you find that your audience is a mixed one in which there are people of different disciplines, but still they are all from the scientific community, you can still talk more freely, but would like to elaborate or make clear some of the typical jargons that you may be using typically from the field of nanotechnology. But supposing you're talking to an audience which is a non-scientific audience, people who are, let's say laymen, and you're just trying to talk about the wonders of nanotechnology to such people, I believe you need to talk in layman's language. And there you may have seen how these scientific theories and scientific inventions are presented and projected in school books at first standard level, fifth standard, 10th standard. I mean, how through some stories, interesting stories, the small children are made aware of the wonders of science and technology. And as you grow, the language of science and technology changes. It becomes complex. Fine. It turns more scientific. So, friends, the point I'm making is, if you know your audience, probably you will be better prepared. So if I have to quote an example from the game of cricket, if the Indian team has to go to South Africa, it will practice and prepare for hard and bouncy pitches, not for spinning tracks. When some team visits India, they will be preparing for slow, low and turning pitches. Because, there is a character. Fine. So if you prepare for spin and go to South Africa, you are likely to be comprehensively defeated and outwitted. So likewise, friends, the point I'm making is, if you know your audience and you have prepared well, you have less chances of failure and more chances of success. Fine. So you prepare your material in such a way that there is enough for everybody. If you have a mixed audience, there must be something for everybody. Otherwise, some people will not be interested in your speech at all. Now, practice your speech. We always, recommend that you start practicing in your own accustomed world, in your own comfort zone. Fine. So what do we mean by that? When we have to give a speech, we first of all share it with the most intimate friend and seek his honest opinion. Arey yaar, thoda dekho, how am I presenting? Am I making a fool of myself? Am I sounding okay? Do you think I can present? Once we get the feedback, we can probably enlarge the group to 5 or 6, good friends, close friends. Because, suddenly, there are stages. I just today morning I was reading about prodigy, very much like Sachin Tendulkar somewhere in Madhya Pradesh. There is a 13-year-old child who has been, amassing runs like anything, triple hundreds, over 400 also is made in an innings. And people are saying that he is second Sachin Tendulkar because he was also spotted like that when he had 694 run partnership with Binod Kambli. And both of them had been, spotted in school cricket by the experts. Now, maybe this boy is amassing runs like anything, but still straight away he will not be drafted into the Indian team. He may have to go through stages. Fine. So you may have to go through age cricket, under 13, under 15, under 16, under 19, and Ranji Trophy, and other such competitions in order to be eligible to play for the country. So why this is required? Because there are stages. So at once you cannot address a crowd of 1000. You need to practice in your own den, in your own comfort zone, and then open up gradually. And then only you will have courage enough to stand. Fine. Then, it is also said that if you have to take control of your body and control your anxiety, you need to practice a few relaxation techniques. So people say that the moment you reach, take a couple of deep breaths, which calms your nerves and, allows your brain to function more properly. And because, your heartbeat will also turn normal, and that way you will be able to concentrate. And there are so many other such exercises, yoga, meditation, other sorts of exercises also people say. While sitting, also sit comfortably with your back straight. If you recall the last class, I said that, that shows that the flow of energy from your Muladhara chakra is unabated to your, brain. Breathe in slowly, hold your breath for 4 to 5 seconds, then slowly exhale. These are some of the exercises or coping mechanisms, we can call it. These are relaxation techniques, and this is not for the day of presentation. This is to relax your nerves before presentation. Fine. So if you practice them, they will calm your nerves and you will be in a better frame of mind. Imagine yourself walking confidently to the lectern as the audience applauds. As I said, that you close your eyes, you visualize the occasion. Imagine yourself speaking, your voice loud, clear and assured. Sometimes we used to practice it in our own closed rooms, speaking aloud as if we are addressing a large gathering, and that used to give us a lot of confidence. Realize people want you to succeed. All audiences want speakers to be interesting, stimulating, informative and entertaining. And mostly the audience is not hostile, so they may be supporting you. So even if you are a little nervous, don't worry. Everyone makes mistakes. It's common to make mistakes, and audience will forgive you if they find you making a sincere effort. Because, to err is man, to forgive divine. So if we don't make mistakes, we are not humans. We become divine. Fine. But we need to be humans. And we need to be humans in the sense our presentation should also not be something like recorded speech. It should show enough signs of dynamism, dynamic speech. So, you sometimes deliberately also you can make some mistakes because that will make you human. If the fear of public speaking causes you to prepare more, then the fear of speaking serves as its own best antidote. As I said, failures are welcome because people say failures are pillars of success. Provided we take our failures in positive sense. If we are not able to cope up with our failures, unfortunately, we will not be able to succeed in life. Life is not about success alone. It is also about handling pressure, handling failures. And if you go through the life accounts of all the great people, you will realize that they have all been worst of the failures in their initial phases of life. So one thing is loud and clear, that failure is a step towards success. So if we have fear in our mind, that fear will act as a stimulant, as a catalyst, and will help us prepare better and make our mark in subsequent presentations. So, I mean, this is a welcome thing. You should not fear stage fear. So you need not to apologize for being nervous, because it's most of the time your nervousness will not be visible to other people because you will be standing at a distance. If you don't say anything about it, nobody will even notice because they will find it normal only. If you mention your nervousness or apologize for any problems you think you have with your speech, you will be just calling their attention to it. So don't do that. Had you remained silent, your listeners may not have noticed it at all. So there is no need for you to give any kind of explanation. Gain experience, experience builds confidence, and this is key to effective speaking. So most beginning speakers find their anxieties decrease after each speech they give. Friends, let me tell you one thing. You can use your tutorial classes as a platform to build your confidence. And I am telling you what I have experienced all these years. I have seen that the guys who are not able to even introduce themselves in the first class, by the time we ended the semester, they were able to present themselves for 2-3 minutes. And that was, that was a sense of accomplishment for me also as a teacher. And by the time they, passed out, they were able to confidently manage themselves in English and walked out with good jobs. So good job offers. So friends, and IITs provide you that kind of atmosphere and platform. As I said earlier also, कि आप में से बहुत सारे ऐसे मित्र होंगे जो डिसएडवांटेज्ड होंगे ज्योग्राफिकली और अदरवाइज, और जो वर्नाकुलर मीडियम में पढ़ के आए होंगे, लोकल मीडियम में पढ़ के आए होंगे, और उनको कभी कभी ऐसा लगता होगा कि आईआईटी में तो सिर्फ अंग्रेजी चलती है, हम कैसे कोप अप करेंगे, हमको तो फिजिक्स केमिस्ट्री भी समझ में नहीं आ पा रही है क्योंकि वो लोग अंग्रेजी में पढ़ा रहे हैं। तो उनको मैं ये कहना चाहूँगा कि जैसे मैंने पिछले क्लास में कहा था कि आप कोई भी एक अच्छी सी ग्रामर की किताब ले लीजिए और उस ग्रामर की किताब से पढ़ना शुरू करिए और आसपास की जितनी भी चीजें हैं उनका अंग्रेजी नाम जानने की कोशिश करिए। इससे आप में बहुत ज्यादा कॉन्फिडेंस आएगा और आपके पास बहुत सारे शब्द भी आएंगे। सो यू कैन स्टार्ट बिल्डिंग। हाँ, बहानेबाजी अगर हम करेंगे कि अरे सर हमको तो आता नहीं, हम तो हिंदी मीडियम से आए, हम तो आप लोगों को मैं क्या बताऊं कि मैं भी हिंदी मीडियम से आया हूं। 12th तक मैंने भी हिंदी मीडियम से पढ़ा है और मैं आईआईटी में प्रोफेसर हूं। तो मुझे अब आपको ये बताने की आवश्यकता तो नहीं है कि अगर हम लोग सीरियसली प्रयास करें तो हम क्या नहीं कर सकते। तो such friends will be having more of stage fear, and their fear will not be because of less exposure. Their fear may be because of language. They may be speaking fluently and confidently in their own language. They may be, the apple pie of their friends, but they may be hesitant to speak in English because their English will be deficient in their own assessment. तो उनकी प्रॉब्लम अलग है, क्योंकि वो गांव वगैरह के जो बच्चे हैं थोड़े ओपन हार्टेड होते हैं, तो लोगों से बात करने में उनको ज़्यादा दिक्कत नहीं होती। लेकिन स्टेज फियर इसलिए होगा कि कभी फॉर्मल सेटिंग में उनको ऐसा माहौल नहीं मिला, और दूसरे वो अंग्रेजी में कहीं बोलना है इसलिए ज़्यादा प्रॉब्लम है। हिंदी में बोलना हो तो शायद वो और कॉन्फिडेंटली बोले। So, as I said, each one of us may have our own share of problems and our own reasons to feel stage fear. So we need to identify those reasons and we need to rectify them. So you need to concentrate on your message, not the medium. Many a time while evaluating, we look at the message of the students. And I have given excellent rating to students whose English was not top class, but still the message that they were trying to convey were excellent. Fine. So their messages were excellent, and that's why. So you concentrate on what you want to talk about. Don't concentrate on what kind of language are you speaking. So your nervous feelings will dissipate if you focus your attention away from your anxieties and concentrate on your message and your audience and not yourself. Fine. So most of the time we start, thinking, how am I looking? मेरा ड्रेस तो ठीक है, कहीं मैं जैसे खड़ा हूँ अच्छा तो नहीं लग रहा है, मेरी आवाज अच्छी आ रही है, नहीं आ रही है, इस वजह से प्रॉब्लम होती है. Think like a good host. Take attention of yourself and take care of your audience, and rest your audience will take care of you. This is the simple, way you can control your fear and turn even the most hostile environment into a conducive one. Fine. So you can turn your nervousness into positive energy. The same nervous energy that causes stage fright can be an asset to you, because that will compel you to prepare more and more, and that will make you stronger with each presentation. Harness it and transform it into vitality and enthusiasm, and don't allow you to mar your presentation skill. अब देखिए कैरेक्टर क्या होता है. अगर कोई क्वालिटी बैट्समैन होता है तो वो सोचता है कि चलो हमको आप ऑस्ट्रेलिया में गाबा के पिच पे हमको आप एक मौका दे दो, मैं आपको दिखा दूंगा कि मेरे में कितना गट्स है. और जो ऐसे टुटपुंजिया होंगे वो कहेंगे कह रहे हमको फिरोज शाह कोटला पे खिला दो पाटा विकेट पे ताकि हम शतक मार दें. लेकिन लंबा कौन जाएगा? लंबा वो जाएगा जो चैलेंज लेता हो, जो गाबा में जाके टिक जाएगा ना, वही लंबा खेलेगा. So the thing is, if you turn your nervousness into positive energy, you will certainly make your, future presentations better than the last one, and a day will come when you will be rated very high as a presenter. Fine. So things you shouldn't do. I mean, these are the distractors. These are the things that contribute to your stage fear rather than taking care of it. Well, don't read directly from your notes. I mean, people never take it seriously, and they don't think that a good speaker can do that. So you name any of the great speakers and you will find that they all speak extempore. Although we don't, recommend you speaking extempore in a professional presentation because you have to be accurate, but still we want you to prepare your private notes but put less material on your PPT. Speak on 10 words and look at the 10 words and speak 100 words. That kind of, preparation should be there. So don't read directly from notes. except glancing at them. Reading directly from screen, except the points, will always turn you into a very, very poor speaker. Fine. Never turn your back on your audience. Audience should always be in your complete view. Slouch or keep your hands in pocket, that is considered a defeating gesture. Using pause fillers is also not a good idea. And mostly people do it when they are short on ideas. So when the next point is not coming to you freely, you buy time by saying, yes, I know. So professional presentations should be such that everything should shoot out of your mouth, should be crisp. Okay, it should be crisp and seamless. We would not like to see those boring silences in between or lot of use of speech mannerisms. Don't make any kind of nervous gestures, like, sometimes you do it unconsciously as well. You start doing this or doing this or something, Never make any bad comments about your audience or insult them, because that way you will be spoiling your relationship. So always be positive, always say nice things about your audience. Even if they are a little unruly, then also you need to control them, not by brute force, but by your persuasive, ability. Fine. So you need not to shout at them if they are making noise. Rather, you need to control them psychologically and otherwise. Don't talk too fast or too meekly. I mean, both of these things are not recommended. If you are speaking too fast and the words are not clear, people will always find difficult to understand. If you are speaking too meekly and you are not audible, then also people will not value your presentation. So things that you should do. First of all, always maintain a proper eye-to-eye contact with your audience, because that way you will always remain connected. But yes, don't look at one person in the audience. Look at everybody evenly. So your movement should be like a rotating light, and it should be, throwing itself on the different sections of the audience evenly, so that nobody feels left out and nobody feels, special. So staring at people, there will be a connection of feeling that will arise. Side by side, you can also glance at your notes. You always make appropriate gestures, because gestures are wonderful in reinforcing an idea. Because just try to understand that people have, limitations of their retention of memory. So sometimes, when you are speaking for 1 hour or half an hour, their attention is diverted. At that point in time, your gestures might, act wonders, because of gestures, they will understand what is being said. Speak about what you are passionate about. Mind your language, tone and body language. So friends, that is the reason, when I give an example from the game of cricket, I always feel confident because I'm so passionate about it. If I bring some example from some other field in which I'm not interested, maybe I may not be that confident or passionate about what I'm talking about. So jokes are good, but don't become a laughing stock. So if your serious presentation turns out to be a joke, that is not good. Rhetorical questions may be used as props. What do we mean by rhetorical questions? These questions are questions that don't require answers from your audience. You just throw some question and don't expect an answer from the audience, but these questions are used as props to build relationship, to involve your audience, and always use a strong opening and a strong closing. Strong opening, you might start with a story or a quote or a question, an interesting statistic, or strong closing depends on the purpose of speaking. So you can tell your audience what you have been talking about and how this matters to them and what next. Fine. So you can use something impressive or motivational to end your talk so that people leave the hall with good feeling. And last but not the least, friends, let me tell you, great speakers are not born, they are trained. So each one of us has potential to achieve that greatness despite all limitations. Limitations of upbringing, limitations of opportunities, limitations of language, limitations of every kind. So with this, friends, I'd like to end this topic. Thank you very much. I welcome your comments and feedback. Yes. Any questions?
Sir, how to handle
How to handle
overthinking?
overthinking? See, overthinking, I mean, it's difficult because it is part of nature. There are some people who have a typical habit of thinking and more thinking on anything. Now, I guess that this can be controlled if you divert your attention. Fine. When something is troubling you and you are thinking day and night about that, you turn your attention to something else. Again, rather than allowing yourself the luxury of loneliness, you try to join some people's company. So that way your attention will be diverted, and this tendency of overdoing something or overthinking on a topic will also, not end completely, but certainly will improve.
Okay, thank you.
Thank you. Thank you. So can you give me 1 hour so that I can discuss group discussion, because that may be part of your midterm examination. So can you just suggest me 1 hour slot somewhere? Even it's a small topic, it might take 45 minutes or so.
Should the CRs just discuss and
Yeah, please let me know, or otherwise, if you don't do that, I'll put the slides on team. But I'd like to talk about that, okay?
Yes, sir. We'll discuss about this and we'll let you know today.
Yeah,
Sir.
please let me know. Please let me know. Okay, thank you. Thank you very much. Thank you,
Sir,
everybody.
but they are already conducting the GD.
Okay, no, I mean, can you answer questions regarding GT? If you want, I can upload my PPT. Okay, no,
yes,
I mean, can you answer some theoretical questions regarding that? Do's and don'ts.
Means the topic will be the lecture that you.
No, if you want, I can upload my slides. I'll upload my slides on GT. But
Okay,
if you
sir.
allow me, I can, I mean, if you provide me a time slot, I can explain them also. Please let me know, okay, in a day or two.
Okay, sir. Sir, if you can just upload the slides today itself, so we can just have a look through them. If we find that we need like real explanation, so we'll let you know about the time slot for the class.
Yeah, Param, I'll do that. I'll do that.
Okay, sir. Thank you, sir.
Okay, thank you. And all slides will be available on Teams. So those who have not tried to find out, I have already uploaded the earlier slides. Fine. Okay then, thank you. Thank you very much. Thanks for joining.
Thank you, sir.
Thank you, sir.